Welcome to solverfy.
All right, so first of all, notice that when you've got a number n, you can always write it as n equals 100a plus b. I mean, a could even take the value 0 for the first values, but you can always write it in this form here. The reason I'm saying this is that n squared is equal to 100a plus b squared, which is 10,000 a squared plus 200 ab plus b squared. Now notice that this number here will always have the last two digits being equal to 0, 0, all right, because you've got this 10,000 here. And now here again, since you've got 200, the last two digits of this product here will also be 0, 0. So what we've just shown here is that you only have to consider the b basically of if you decompose n in this shape, where let me just precise that b is between 0 and 99. Well, by checking only the last two digits of n, well, you can know the last two digits of n squared. And that's already a big step, because if we're trying to show something for all n, we're basically trying to show it for an infinite number of values, which is not something possible in if you want to prove something by exhaustion, or prove something by doing a proof by case. And now we've reduced it to 100 different cases. So one way of doing it would be simply to check for all the different values of b ranging from 0 to 99, of b squared, sorry, where b ranges from 0 to 99, and conclude. But that is obviously very, takes a lot of time, and it's quite boring. So what you want to do is to reduce the number of cases to check by you want to further reduce the number of cases to check. Now, why exactly did I jumped straight into this decomposition? Well, intuitively, you got to tell yourself that, if you've got a number like 683,540, that this part here, when it is squared, it doesn't really contribute that much to the last two digits of the number when it's squared, because these, I mean, this is a fuzzy argument again, but this is often what leads you to some form of a more rigorous proof. Okay, all right, so that was a short parenthesis. So how do you reduce the number of cases to check once you've established that you only have to look at b ranging from 0 to 99? Well, the first thing is to notice that 100 minus b squared, right, is equal to 100 squared minus 200b plus b squared. And since you only care about the last two digits, well, again, you notice that this ends in 0, 0. This ends again in 0, 0 by the same argument we've made before. And therefore, the last two digits of 100 minus b squared is the same as the last two digits of b squared. So what does that tell us? Well, basically, we've reduced the number of cases to check by 2. We've divided by the number of cases by 2. Why? Well, basically what this means is that checking the last two digits of a number, let's say 4, is the same as, of 4 squared, sorry, is the same as checking the last two digits of 100 minus 4 squared, which is 96. All right? 96 squared, sorry. And, if you check this, 4 squared is equal to 16, and 96 squared is 9,216. So, you see that both end in 60. Okay. And why do I say 50? Well, I mean, you can see that if, you start with b equals 1, then that tells you that 99 has the same, 99 squared has the same last two digits as 1 squared. then you'd say 2, same as 98, and you go down, and you've basically divided, you've divided those 100 numbers in 2 halves, where you've got 50 on both sides. Okay, now that's already very good. You divide the number of cases by 2, but you can go one step further. And the thing is here, if you notice here, that 2 is, that 2 here is almost too big. It's not necessary. It could even work if that 200 was 100. So what we do is we actually look, okay, well, what happens if I get 50 plus b squared, all right, and 50 minus b squared? The reason I'm taking 50 is that 2 times 50 is 100. So that is 50 squared plus 2 times 50 times b plus b squared, which is 50 squared plus 100b plus b squared. Okay, and I mean 50 squared is 2,500. I can write that down directly. And notice again, by the same argument, this ends with 2 zeros. This necessarily ends with 2 zeros. So all that matters again is b squared. And the same argument holds here. Let's just do it very quickly. That's 2,500 minus 100b plus b squared. Okay? And what we've actually done here is again reduce the number of cases by almost 2. And again, the reason is, suppose we're looking at b equals 4, then what we've just shown is that 4 squared, 96 squared, 46 squared, and 54 squared all end with the same the last 2 digits of these squares are the same. Namely, I mean, we've seen here 16, okay? 16 on both numbers. And if you check 46 squared is that equals 2,116, and that equals 2,916. So again, you find that 16 again. And so why does that reduce the number of cases to check? Well, that reduces, I mean, as you can see, you basically take a number 0, 50, 100. That's one number to check, okay? B equals 0. If b equals 1, then you check 1, 49, 51, 96, going on and on and on and on, and you basically reach 25 here, 26 here, and symmetrically you've got these 4 different blocks, 1, 2, 3, 4, and by just checking b ranging from 0 to 25, well, by the argument we've made here, that suffices to check b ranging from 0 to 100. Sorry, that's 99. 0 to 100. And by the argument made here, the first one, well, that's enough to show all the different possible values, or the values of the last 2 digits of n squared. Okay? Now, I don't think there's a way of reducing it again, so now it becomes a bit tedious. But you can see 0 squared is 0, 1 squared is 1, 2 squared is 4, and you go on and on and on. That's not a very interesting part of the exercise, but if you go on and check this 26 different cases, you'll see that the possible last 2 digits will be 00, 01, 04, 09, 16, 25, 36, 49, 64, 81, 21, 44, 69, 96, 56, 89, 24, 61, 41, 84, 29, and finally 76. Okay, well, and that ends the exercise. Okay, I hope this helped. And